Hey everybody, this is Larry. This is me doing day 28 of the Leetcode Day Challenge. Yeah, right, and now week 5. Yeah, we did the contest earlier and I kind of just forgot about today, so hopefully this is the time to catch up. And we have a hard problem. 20:45, second minimum time to reach destination. Hit the like button, hit the subscribe button, join me on Discord. Let me know what you think about this one. Let's take a look at what this one is. If guessing from the title, I think it's a good problem, but yeah. Let's see. At most one edge. There's just a graph setup. Green to red, and change each word. What? Each word has a try. Okay, I'll change at the same time. Can enter, but I can only leave when it's red. You cannot wait at a vertex if it is green. Okay, this is maybe not quite the one that I was thinking of, but though the second minimum value is well, it's something else anyway. Though it has to be strictly larger than for some reason. Yeah. Okay, so I don't know what this thing about green is or whatever. Oh, change. So I mean, I think this. This is a shortest path problem for sure, right? Sorry, I'm like trying to find my pencil. I don't know what happened to it. Anyway, but yeah, this is a very clear shortest path problem, and the thing that we just have to handle is just there are a lot of weird conditions that we have to be careful about that dictates the implicit edges that are or additional conditions about these edges that allow us to do the math, right? So that's basically the idea. Definitely, I don't think conceptually is that hard, but yeah. Yeah, but it's just about being careful on a lot of things. Okay, first thing we want to do, I guess, is just do the adjacency list. But the two things that we have to kind of be careful about. One is the second minimum thing, right? And that's actually not super bad. We can just keep track of yeah, the key part about Dijkstra's algorithm, which we I guess kind of did. I mean, the last couple of days we did Floyd Rorschach, but for Dijkstra's algorithm, the key thing to remember about it is, or one of the key things anyway, is that it is greedy, and as a result, the greedy actually also holds for the second minimum value. Just kind of keep track of more states, so you have to be careful, of course. And yeah, so I think that's one thing. Yeah, what is this? What's time and change again? Oh. What is time and change? Did I miss it? Oh, it's not in bold for some reason. That's why I was like trying to find time. Oh, any edge is time minutes, and it changes every change minutes. Okay, it's a very weird problem, but that's fine. So actually, the rate is always time, which is kind of weird to be honest, but maybe not. I don't know. Okay, we're trying to get from 1 to n, so it's also 1 based, but maybe for me, I don't care about. I always like to do it 0 index. Maybe that's just the way I think, so we'll think about it. But yeah, but first, let's create an adjacency list, right? UE in edges, adjacency list of u dot append we, and so forth, right? Just kind of keep it to the things that we care about for now. And then I think that's all we really need to kind of set up Dijkstra. Yeah, I mean, I think we just have to be really careful. I don't think there's anything that tricky about it. So then maybe you could have distances. Let's just call it 1, right? So we have infinity times n, and then distances of 2, also infinity times n. And you can, of course, use a 2D array. It doesn't matter that much. Or like, you know, an implicit or explicit dimensions, I don't think it matters that much. Maybe you could write it a little bit cleaner. I don't know. But yeah, and then now we start at, you know, wherever. Well, it's not a queue, it's a Dijkstra's, right? Because I mean, I don't know. I think yeah. I mean, maybe you don't need Dijkstra's, but of the way like time and change is set up, but I don't want to think about it, honestly. So I want to just do Dijkstra and we'll see where the things fall, right? So okay. So yeah, so then we have a heap, right? And then we have let's push to the heap. We want to say we start at node 0, at time 0, node 0, and is that it? Yeah, I guess that's it, right? I mean, what else do we need? And then, while this is true, we pop, right? We have, what is it? We have the current time, which is the distance, let's say is t, d, sorry, and node is this, right? Okay. I'm trying to think. What is the best way to? I'm not gonna lie. I remember this as being a kind of a studied problem for the second min, but I forget the exact detail. Which I mean, you shouldn't solve these problems by memory anyway. You should try to solve them. But I'm trying to right now think about the principles that I need to care about to get D. Right. But there are basically a couple of ideas. And I'm trying to think whether we need to encode whether this is the smallest or the second smallest in here. Because the idea here is that, well, in a greedy kind of way, of course, the shortest path, and this is in general, so nothing about the second minimum time, but the shortest path is going to be built off on the shortest path. Like I said, that is the core basis of greedy, right? Shortest path plus shortest path gives you the shortest path, or like the potential, right? Because there's no you could do a very quick proof by contradiction or exchange or whatever, where if you have the shortest path plus the second shortest path, well, there's no way to get the shortest path from that, right? So that's basically the idea. Yeah, I don't know if I don't know if I need an explicit one. So maybe we do. Yeah, maybe it's okay then. But yeah, we want to write right, this equals 0, right? And let's just say this is the 0th shortest path. So maybe this is just like the index of the shortest path, right? I don't know if we need it. Maybe if I don't need it, I don't need it, and I'll take it back. But basically, we can say something like, because we want to be able to early terminate. So we want to if this is and maybe this is where having I like having two distances for explanation purposes for YouTube's, so that I can it's more clear versus like a two-dimensional array. So let's keep it this way, even though it makes the code a little bit yucky. But yeah, if index is equal to 1 and distances of node is greater than D, then we continue, right? And then same if index is equal to 1 and distances of 2 of node is greater than D, then we continue. Otherwise, well, we just look at all the edges, right? For v in adjacency list of the node, what happens? So basically, yeah. Yeah, basically they're just doing the check, right? So the thing about the edges is that it's a little bit wonky with these change in time. So that is just a extra layer of complexity. Not that bad. We just have to do the math, right? So the new distance is equal to time plus D, kind of, right? Because the D is the current time, and we can only move with this green light. So is D a green light, right? You can now wait at a vertex if the signal is green. That part I don't know. I guess you cannot wait that long. I don't know why I don't know. Doesn't matter, I suppose. But yeah, so then now we want to see if it's green, right? So given that change is the time it gets from green to red and vice versa, that means that change times 2 is the cycle, right? So one loop of green to red to green, right? So here maybe we can do the math on, okay, so this is D, so is this green, right? So let's just say cycle is equal to change times 2. D mod cycle, so let's say D mod cycle is good, because yeah, all the it just loops, right? So then if you mod it by cycle, then if this is less than or equal to change, is it less than or equal to? No, because it's 0 index, right? So if this is strictly less than, then this is green light, right? So if this is the case, then we can go now. So the new distance is equal to D plus time, right? Else, this is red light, right? Then what happens? Then we have to go to the next D, right? So basically, yeah, so that means, so then now we have, basically you want to do something like round divided by cycle and then round up, right? So something like this, but then round up, right? So this is the new distance. So this is when you, wait, is this right? No. Well, this is the number of cycles, and then it's this times cycle. So okay, I messed this up. So it's round up, right? So it's just D plus cycle minus 1 divided by cycle, right? So this is the new distance before we add the time. So then we just add time, right? And this number, just to be clear, is just equal to CL of D over cycle. You could prove to you, I mean, I'm not gonna go over it today in this video just because it's really late and I don't know, I messed up. But yeah, you could kind of just play around with it. I feel like this is not one of those things that you explain. If you should actually see the visualization and why it works, then it'll tell you. And also keeping in mind that yeah, if this is 0 or 0 mod cycle, then you know this is just still D. So yeah, so that's what basically this happens, and then we get to the next green light, and then we add time for the traveling time, right? Okay. And then now we want to see if yeah, if this time is better than, I mean, I think you can, like I said, you can make some minor optimizations, but we don't even have to think about that much yet, right? For now, we can just go. And also, I think one thing that I actually forgot, or I don't know, right, is that this is going to be the same no matter what edge we travel to. So we can actually just take it out so that we don't do this, you know, multiple times, right? Yeah. So then now we go if ND is, so now we're trying to go to V, right? If this is smaller than distances of 1 of V, right, then distances 1 of V is equal to ND, and then we heap push it. H of the new time is new D, terrible naming probably, V and 0, right? And then else if ND is less than distances of 2, yeah. And keeping in mind, this is very weird that it's strictly larger, to be honest. But so yeah, the code is with that in mind. Hopefully everything I'm saying is true. Otherwise, it's just very confusing. But yeah, and that's pretty much it. And then here we return -1 if we cannot get to the end. I guess it's connected. So maybe we can just do like an assert force type thing. But here we want to say, oh, to n, right? So yeah, so if index is equal to 1 and node is equal to n minus 1, then we can just return D. that's pretty much it. Right. Oh, this is wrong. I did remember. I don't know why I'm so bad at remembering stuff. Because I had a mental note. But yeah, if this is smaller than this, we update the distance, but we also actually want to update, you know, we want to push the what used to be minimal, now is the second minimal, right? So that's basically the idea. Yeah. Let's give it a spin. Ooh. Tell me why. So that means that this loops before. Do I mess up? Maybe I mess up somewhere. Maybe this doesn't. Oh, well, no, that should be fine. Okay. Huh. Alright, let's point out some random stuff. Don't know why, honestly. So we'll see. Maybe it's just some silly typo things, which happens a lot. Yeah. So it doesn't seem to go to any other edges. Which is, you know, not a great thing. Do I do it here? I go to here? Yep. So then cycle, we go to cycle. Okay, so then now what? So this doesn't. Do I mess up the adjacency list? Oh, I lied because I said that I was going to convert it to 0 index and then I forgot. Okay, I mean, at least it is now correctly incorrect and not just like, oh, what the, that's not good. But all right. Oh, the second can keep going, but don't I keep going? Oh, because I've set distance of 2 is equal to infinity. Okay, fine. Oh no, this is okay. At least this is, you know, it terminates, which is good. But why do I think it's 7? So 1 to 2 is 3, okay. And then 1 to 1 is going. So each cycle is 4. We're at 3 at 2. So then we get to 1 at 6, right? Yeah. But then we cannot go until it's 8 again and then go. Okay. I mean, I know what the numbers should be, so we'll see why this is not doing it right. The 2 inputs. I mean, I do like that, you know, this is a good, easy one to debug in theory. Right? Oh no, I'm missing a thing. Okay, so 0, 0, 0, 3, 1, node 1, index 0, yep, that's the shortest path is 3, and then it goes back to the first path is 4 from 0. That's not right. Did I mess this up? D is 3. Maybe my calculation for ND is wrong. I don't know. Let's see. So 3 goes to 4. That is definitely not right. This is not round up. Oh, this is just we have to times it by cycle. I am an idiot. Because that's the number of cycles round up, and then we have to add multiply the cycle to get the correct time. Man, I am like really, I don't know. I mean, I guess today at the very least I can say it's late, but I am not doing well recently. I feel like for some reason I'm just like very sloppy. Like this way. Ooh, okay. I mean that's. I was gonna say that's fine, and it is, but it's just like so annoying to debug. It seems like. That means that my answer is way better. That means that some of the math is wrong. This is the number of cycles plus time. That sounds okay. What is my inputs? What are my inputs? 946, 183. So it feels like it's a cycle thing again. Because, I don't know, let's see. Uh, 2044, right? And then the next one is 3142. But, so we returned it one thing earlier. But it's not really possible to do it one thing earlier. Because it's 520, so we're gonna go 5919. It's not possible to, because basically this is 2 cycles, and it's just not, yeah, not really possible. Am I doing something wrong? Let me think. Well, this is just weird, the way that this, because that probably should not be true. Oh, I know. I think I do this update like this, but I have to do it so that because if ND is equal to distance of read of, yeah, okay, that's just sloppy again. I thought I did it intentionally, but yeah, but we have to write that it is not equal to yeah. That is sloppy because because if they're the same, this is false, but this is true. This would have been true. I don't know. Like I said, I don't know why I've been just sloppy. Having a terrible one, but I don't know. Maybe it's. I think honestly, I think it's just the running. I've been running too much, and maybe it's just mentally draining for me. I don't know. My hair's a little bit funky. What is going on here? Anyway, yeah, I mean, this is just Dijkstra. The way that we kind of did it is just by having two nodes. So you could kind of think about it as a duplicate nodes, right? With edges in a way, whatever way. So it's just 2 times n for Dijkstra, which is just, you know, still n log or v log e if you want to call it that. So very Dijkstra complexity because we only double the number of nodes and edges, I guess. But yeah, that's all I have with this one. Let me know what you think. Thanks for watching. Have a great weekend, everybody. I'm gonna enjoy taking a sleep. Taking a sleep. That's barely English. Anyway, I'll see you later and take care. Bye bye.